Let's do ionization energy's evil opposite twin, and that's electron affinity. Ionization energy is the amount of energy it takes to remove an electron. Electron affinity is the change that occurs when an electron is added. If we wanted to be very formal about it, we would say that electron affinity is the energy released Electron affinity is the energy released when an electron is added to an atom in the gaseous state. The reaction associated with it would be element in the gaseous state plus an electron yields a negatively charged cation in the gaseous state plus energy. An important difference between electron affinity and ionization energy is electron affinity is exothermic. The addition of an electron releases energy. Remember, we had to pay an atom to remove an electron with ionization energy. Well, now we're giving an atom an electron, so it just makes sense that the atom would pay us energy, right? So electron affinity always releases energy. Here is a graph for electron affinity. First, notice something a little bit odd here. Notice that we have these negative signs here. Electron affinity is technically a negative quantity because in chemistry we use positive and negatives to denote the direction of energy flow. And negative means energy is leaving the system. Since our atom is releasing energy, it's losing it, so it's negative. That's why we see the negative there. The more an atom wants an electron, the more it's willing to pay for it, right? It's kind of like an eBay auction. The more you want something, the more you'll pay for it. Same for an atom. The more it wants an electron, the more it'll pay for it. So that means the higher the negative value. In other words, this is the greater, quote unquote, this is the greater electron affinity compared to this, even though numerically it's a lower number. Because these guys have great electron affinity because they're willing to pay a lot. These guys have low electron affinity because they don't want to pay you anything. Who wants electrons the most? Who's willing to pay? If we look at our graph here, who are those guys? Those are our halogens with our high electron affinities, our group 7A. Who has our low electron affinity? Kind of scattered in there, but you see our low electron affinity is our group 1A, and our lowest is our noble gases in group 2A, and there it's kind of a mess. But your reality, your electron affinity is going to follow the exact same trends that we saw for our ionization energy. Electron affinity is going to increase this direction, except for noble gases. Noble gases is going to, let me put it this way, 1A to 7A electron affinity will increase. Your noble gases, they already have a complete set of cards, right? They have zero electron affinity. They're all right there on your 0 line. So your ionization energy, your electron affinity increases across a period as you go left to right. Because your effective nuclear charge increases, right? And the more effective your nuclear charge, the better you can attract electrons. So electron affinity is also going to increase up a group for the same reason. So once again, your summation error for electron affinity is going to be the same as it was for ionization energy. The only bumps you're going to see in electron affinity are going to be those bumps seen by ionization energy, but in different spots, but for the same reason. What did he just say? Here, let me work an example for you, or show you an example. Clean it up a little bit here, and then we can zoom in on our chart again. And let's narrow it to just one period here, where we're looking at atomic number. Alright, let's find our period. If we look here, here is our first period. Let's label our elements here. We have lithium, followed by beryllium, followed by boron there, followed by carbon there, nitrogen there, and then oxygen there, and then fluorine. You can see the general movement of increase as we go left to right. However, we see those two bumps again, but our two bumps have shifted location just a little bit. We see our hiccup in the trend going from 1A to group 2A. For ionization, for electron affinity, group 1A has a greater electron affinity than group 2A. Why is that? It has to do with that subset of baseball cards again. Lithium has an electron configuration of helium 2s1. Beryllium has an electron configuration of that. If beryllium, so if we think about it from beryllium's perspective, beryllium's already completed their subsets, right? They all have the foil Pokemon cards, right? They have the foil subset. If they get another electron, they have to start a brand new subset. Ugh. Right? If they'd have to put one in the P, so they'd have to start a new subset if it formed beryllium negative. So it doesn't really want that extra electron. It would have to start the whole collecting process all over again. So beryllium's not really interested in gaining that extra electron. However, lithium, if it gains an extra electron, then it completes its subset. Right? It completes its 2s. It wants that subset complete. It wants that subset complete either by losing the electron or gaining one. Because gaining an electron completes that 2s sublevel, the electron affinity for 1A elements is greater than the electron affinity for group 2A elements. So that's one place where we see that hiccup, from lithium to beryllium. Look where we see our other subset, our other hiccup, carbon to nitrogen. And this time it's going to have to do with that half-filled subshell, just like we had that half-filled subshell issue with ionization energy. If we look at carbon, carbon is helium, 2s, 2, 2p, 2. If we give it an electron, or it buys itself an electron with electron affinity, then we have carbon negative, helium, 2s, 2, 1, 2, 3, 2p, 1, 2, 3. And it's halfway through its set, right? If it gains an electron, then it has one electron in each one of its 2p orbitals, and it has that nice parallelism of a half-filled subshell. It's happy, it likes that. However, if we try to give an extra electron to nitrogen, we're ruining a perfect situation. Nitrogen's already happy, relatively speaking, because nitrogen has a half-filled p subshell. If it takes an extra electron, then it disrupts that nice symmetry pattern it had going. So nitrogen wants that electron a lot less than carbon does. The electron affinity for group 4A elements is greater than the electron affinity for group 5A elements, carbon, nitrogen. So that's where we see our second hiccups. You're responsible for knowing those hiccups, and you're responsible for being able to explain why those hiccups occur. Why don't you write down, now's a good time for you to write down Michael. Write down Michael. Michael Scott. Write down Michael. Michael Scott. Which of the following has the greatest electron affinity? Well, we said electron affinity increases that direction with a couple hiccups, and these are all far enough apart that we're not looking at that hiccup situation. For example, here we're looking at group 4A, so it's not that hiccup, and we're looking at group 1A, it's not group 2A, so there's no hiccup there, so it's a straightforward that-way pattern. C has the greatest electron affinity. Chemistry's easy, life is hard. Beep.